Good afternoon, Namaskar, welcome back to the NSUT studio channel. I am Dr. Pinaki Chakraborty. The topic of today's lecture is computer science and computational thinking. Computers distinguish themselves from other man-made devices by the level of sophistication in their design, their wide range of applications, and the theoretical foundation of their working. Computers have been evolving steadily for the last 8 decades. Advances in computers have been complemented by developments in computer science, which is perhaps the only academic discipline focusing on a single man-made artifact. Computers and computer science can influence how people associated with them think and behave. In this lecture, I will not provide any new facts, but will share my opinion on this topic. I have formed my opinion on this topic on the basis of my reading of the literature and discussions with my professors, peers, and students. I am going to summarize what I have learnt on this topic in the last 20 years in the next 20 minutes for you. If you want to learn more about the topic, then please read my article, the reference of which is given at the bottom of the screen. According to ancient Greek mythology, Proteus is the god of the sea and characterizes its constantly changing nature. Seymour Papert compared the versatility of computers with the various manifestations of the sea god. Here we must appreciate the fact that Papert was able to realize how useful computers can be way back in the 1960s and 1970s. Technologically, a computer is a machine which can execute programs. A program is a sequence of instructions presented in a predetermined binary format which we call the machine language. A program can be used to find the solution to a problem which is difficult to solve manually. Such programs can be written to solve problems in different fields of human endeavor. These make computer powerful and perhaps the most versatile machines in the world. The first computers were built in the 1940s. Z3 and Z4 computers built by Konrad Zuse in Germany and ENIAC and EDVAC computers built in USA were among the first computers. Since the late 1940s, almost all computers follow a model popularized by John von Neumann. According to this model, also known as the von Neumann architecture, a computer has a memory unit which stores programs and data. The processing unit of the computer fetches one instruction from the memory, decodes it, and executes it. After executing the instruction, the processing unit repeats these steps with the next instruction in the sequence or another instruction elsewhere as dictated by the logic of the program. Since the programs are stored in the computers, such a computer is known as a stored program computer. This technique of executing programs in which instructions are fetched, decoded, and executed one by one is known as the instruction cycle. Instruction cycle is a characteristic feature of computers. Hence, any machine capable of implementing instruction cycle is a computer. Commonly used computers include desktop computers, laptops, tablets, smartphones, and smartwatches. Etzker Dijkstra remarked that computers are usually electronic machines which can store large volumes of data and process them at a high speed with a high reliability. On the theory front, Alan Turing proposed a theoretical model of computation which can be used to solve a large class of computational problems. The model later became known as Turing machine. Turing also defined a universal Turing machine, which is a theoretical model of computation that can emulate an arbitrary Turing machine. In other words, a Turing machine can solve a particular computational problem, while a universal Turing machine can solve all computational problems solvable by Turing machines. Here it may be noted that Turing actually used the terms automatic machine and universal computing machine to denote Turing machine and universal Turing machine respectively. The term Turing machine was first used in a review of Turing's work by his doctoral advisor Alonzo Church. A device is called Turing complete if it can emulate all Turing machines, that is, if it is as powerful as a universal Turing machine. Computers are Turing complete. Further, no theoretical model or physical device is known to be able to solve any computational problem that cannot be solved by a Turing machine. Therefore, computers can solve all computational problems which can be solved mechanically. Scholars have provided several interesting definitions of computer science. However, the definition by Neville et al. Is certainly the most succinct one. Neville, Perlis and Simon viewed computer science as the study of phenomena surrounding computers. Following the same line of thought, Peter Denning defined computer science as the science of information processes and their interaction with the world. There is an emphasis on the role played by computation in the real world in the definitions of Neville et al. And Denning. Alternatively, definitions by Donald Knuth and Janet Wing are more procedure oriented. Knuth defined computer science as the study of algorithms, while Wing saw computer science as the study of computations, which primarily deals with determining what can be computed and how they can be computed. Among all phenomena related to computers, algorithms are perhaps the most important ones. An algorithm is a finite sequence of steps that can be followed to transform the given input information to the desired output information. A programmer designs algorithms intended for mechanical execution and writes program according to the algorithm in a programming language. A program is actually a particular way of representing an algorithm. Theoretically, an algorithm for a function f is equivalent to a Turing machine that computes that function f. Programming languages are models of computation equivalent to a universal Turing machine and hence can be used to implement various algorithms. Programmers, however, prefer writing algorithms intuitively rather than as Turing machine functions. Computer science was born as an academic discipline with the joining together of mathematical logic and algorithmic theory and the invention of stored program computers in the mid 1940s. By the early 1960s, there was a sufficient body of knowledge to justify the starting of academic programs and even establishing university departments for computer science. In this regard, to the best of my knowledge, University of Cambridge was the first university to offer an academic program in computer science, which was started in 1953, while Purdue University was the first university to establish a computer science department, which it did in 1962. Netaji Subhas University of Technology was established in 1983. The computer science department is one of the oldest, the largest and the most prestigious department in Netaji Subhas University of Technology. Once computer science was established as an academic discipline, universities, including that of ours, played a crucial role in expanding its body of knowledge and disseminating the same among people. Computers are novel and complex equipments which can act as universal computing machines. In other words, computers are tools to implement, study and predict information processes. As a result, computers lie at the center of computer science, and much of the body of knowledge in the discipline is concerned about computers and phenomena surrounding them. Programmers design algorithms and write programs for existing and conceivable computers. For example, Ada Lovelace and Peter Shor designed algorithms for a mechanical computer and a quantum computer respectively, which were conceivable but did not exist at their time. Computer science is, however, more than just programming. Computer science covers understanding of principles of computation, developing working computer systems with hardware and software components, and studying how people interact with them. Seymour Papert is believed to have coined the term computational thinking, and he used it in his magnum opus Mindstorms, Children, Computers and Powerful Ideas. Papert recognized the potential of computers in the field of education, and in the 1960s started developing computer-based tools and techniques to enrich the learning experience of school-aged children. Papert appreciated computers for their utility and versatility. He predicted that the world will be computer rich in the future. He actually wrote that in 1980. He believed that computers are powerful tools which can enable children to explore a wide range of topics. His team developed a device which they named Turtle. The turtle was connected to a computer and could plot lines and curves on a flat surface. The turtle's movement and plotting activities were controlled by programs written in a purpose-designed programming language called Logo. Logo was a simple language and children could write programs in it intuitively. Papert felt that writing programs helped children in two ways. One, children attained mastery over computers, and two, children could connect with various concepts of science, mathematics and arts. It will be interesting to mention at this point that long ago, Charles Babbage also predicted that machines will influence the course of science in the future. Papert believed that using computer as pencil will help children explore and learn new concepts. He felt that computers can help children to think of new ideas and even realize some of them. Papert's philosophy was that children can learn computer programming, and learning to program will influence how they learn other things. It can be inferred that for Papert, computational thinking was thinking influenced by computers, thinking in terms of computers, and thinking to use computers as tools in various activities. Pappert's work influenced scholars from many disciplines for years, but computational thinking did not receive much attention. Things changed suddenly when Janet Wing wrote about her views on computational thinking and the perceived benefits of the same in an essay in 2006. It is difficult to say if Wing was influenced by Pappert's view on computational thinking. Wing did not say anything about Pappert in her 2 articles on computational thinking published in 2006 and 2008. Wing described computational thinking as a universally applicable attitude and skill set that builds upon the concepts of computer science. According to her, computational thinking is taking an approach for solving problems, designing systems, and understanding human behavior using concepts that are fundamental to computer science. Computational thinking allows finding approximate solutions to problems, reducing a problem into another, and solving problems using recursion and parallel processing. Computational thinking is a way of thinking for human beings and not for computers, and can be used by everyone, everywhere. Computational thinking is about conceptualization and not programming as such, and it is an idea, not an artifact. Wing claimed that computational thinking is a fundamental skill for everyone and not just for computer scientists. Wing's work brought computational thinking in the spotlight, and researchers from different disciplines started investigating its utility. Now let us compare the views of Pappert and Wing on computational thinking. Pappert recommended the use of computers as a tool for learners to explore various topics. Pappert's view of computational thinking is concerned about forging ideas and implementing and explaining them. Alternatively, Wing saw computational thinking as an effective way of solving problems in the daily life. Wing's version of computational thinking focuses on abstraction, analysis, and automation. What Pappert and Wing had common was their emphasis on reasoning, and both of them indicated that computational thinking is more than just using computers to solve particular problems. Since Wing published her essay in 2006, researchers started investigating what all consists computational thinking, and several scholars have come up with their own list of components that they believe comprise computational thinking. As I have written in a recent research paper, I think that there are 4 fundamental concepts of computational thinking as follows. 1. Abstraction. A problem should be modeled in a way that highlights computational aspects and obfuscates the rudimentary aspects of the problem space. Such an abstraction is a way of understanding the problem, and it is not bounded by algebraic properties or dimensions of the physical world. 2. Decomposition. A complex problem is divided into simpler sub-problems. The sub-problems are solved separately, and their solutions are combined to obtain a solution of the original problem. Decomposition is often realized using divide and conquer and recursion. In divide and conquer, a problem is divided into sub-problems that are similar in nature and size. Alternatively, in recursion, a problem is reformulated in terms of smaller instances of the same problem. 3. Algorithm design. A basic skill in computer science is to formulate a sequence of computational steps which, if followed, generates a solution to a given problem. The sequence of steps thus formulated applies mathematical logic to obtain efficient, fair and secure solutions. 4. Generalization. Computational thinking is concerned about the application of concepts drawn from computer science to solve various real-world problems. Computational thinking will be more effective if the procedure followed to solve a problem can be reused to solve another problem in some other domain. A vast majority of the world's population today uses computers of some type for performing some of their daily life tasks. Scientists, engineers and professionals in other fields use computers to perform highly specialized work. Computers also provide employment to many people in developed as well as developing countries. In the last 80 years, computer science has evolved a lot, perhaps more than any other academic discipline. Computer science has helped in developing computers with increasing sophistication and in extending their use for the benefit of a growing number of people. Computers and computer science do influence the thinking process of the people associated with them, and we call their way of thinking computational thinking. However, computational thinking can be considered a universally valuable skill, as Janet Wing envisioned, only if people other than computer scientists use it and find it beneficial. Thank you.